In the last video, we have seen how to find HCF and LCM of two numbers using prime factorization. We have also seen a property of HCF and LCM, which is HCF is always a factor of LCM. But there is another one property between HCF and LCM. So let us consider A and B are two numbers. So A is a number, B is a number. The HCF of A and B multiplied by LCM of A and B is equal to A into B. This is a theorem which says the product of HCF and LCM of two numbers, product of HCF and LCM of two numbers is equal to product of the numbers. Let us check this out by using some of the using some example. So let's take example 26 and 91. 26 can be written as 2 into 13. 91 can be written as 7 into 13. So we can say LCM is equal to 2 into 7 into 13, which is 182, and HCF is the common factor is only 13. So we know this. Let's try to prove this theorem. So HCF into LCM, let's find out that first. Product of HCF and LCM is equal to 13 into 182. 182 times 13, 3 2s are 6, 8 3s are 24, 3 1 is 3 plus 2, 5, 2 8 1 6, 4 plus 2 is 6, 8 plus 5 is 13 and 2. So we are getting 2 3 6 6. Now we'll check what is the product of A and B. In this case the numbers are 26 and 91. So 91 multiplied by 21 is 26, 6 1 is 6, 9 6 are 54, 2 1 is 2, and 9 2s are 18. By adding we get 6, 4 plus 2 is 6, 8 plus 5 is 13, 2. We are getting 2 3 6 6. So as you can see, we multiplied HCF and LCM of these two numbers, we are getting 2 3 6 6. We multiplied the numbers itself, we are getting 2 3 6 6. So whenever if in a problem the HCF is known and the numbers are known, we can find LCM. All we need to do is product of numbers and divide it by the HCF of the two numbers. Let us try to solve such a problem. Here it is given HCF of 306 and 9 and 6 306 and 657 is equal to 9, and we need to find the LCM. So LCM will be 306 into 657 divided by HCF value, which is 9. Dividing 9 with 306, 9 3s are 27, remainder 3, 9 4s are 36. So LCM will be 34 into 657. 7 4s are 28, 5 4s are 20 plus 2, 22, 6 4s are 24 plus 2, 26, 7 3s are 21, 2, 5 3s are 15 plus 2, 17, and 6 3s are 18 plus 1, 19. We are getting 8, 3, 13, 12, and 2. Answer will be 2, 2, 3, 3, 8. So using this relation, we can find out we found out LCM in much simpler way with a lot less calculations. So far we have been talking only about rational numbers, but real numbers is of both rational and irrational. So now we'll look deeply into irrational numbers. So irrational numbers has decimal form which has decimal form which is non-terminating, non-recurring. Rational numbers had a general form p divided by q, where p and q are integers and q is not equal to 0. Irrational numbers does not have such a general form. We can mention it like this, like root of a, where a is not a perfect square. This statement is true, very true, but this is not a general condition for irrational numbers, because not only square root of any non-perfect square will give us irrational number, even cubed root of numbers that can be that are not cubes, for example 9 is 3 square, not 3 cubes, so cubed root will be irrational number. Even these are included. Even root of 5 of 25 is irrational. So there is no general form of irrational numbers. So how can we prove root 2 is irrational? We can find out root 2 in its decimal places and say that it is not recurring. Otherwise, there is another one method. The problem with proving this is we don't have a general form for irrational numbers. No general form. But we do have a general form for rational numbers. And the general form of rational numbers is p divided by q. If we prove that root 2 cannot be expressed as p by q, then we will effectively prove that this is rational. So this is how we will prove root 2 is irrational. First step, we will assume root 2 is rational. So now that we have assumed root 2 as a rational, we can find integers p and q such that root 2 is equal to p divided by q and q is not equal to 0. Since root 2 is a rational number, we have assumed that root 2 can be written as p divided by q and q is not equal to 0. So now what we are going to do is we are going to find HCF of p and q and divide it by that HCF, which means we will be getting two new numbers a and b. A is equal to p divided by HCF of p and q, and b is equal to q divided by HCF of p and q. Now that we have divided all the common factors from the numerator and denominator, these two numbers can be called as coprime. Coprime means two numbers which have no common factors. So we have written root 2 is equal to a divided by b, where a and b are coprime. This can be written as, taking b this side, this can be written as b into root 2 is equal to a. Now we will square on both sides. By squaring on both sides, we are getting b square root 2 the whole square will become 2. B square into 2 is equal to a square. So we just got a square is equal to 2 into some other number. What this means is 2 is a factor of a square, because a square is equal to 2 into some other number. That means 2 is a factor of a square, which also means 2 is a factor of a. We have seen fundamental theorem of arithmetic of the factors, prime factors of each number is unique to itself. So since a square is having 2 as a factor, a should also have 2 as a factor. So we have gotten this equation. From this we can write a square, uh, from this we can write a is equal to 2c. We just concluded 2 is a factor of a, so we are writing 2 into some other number is equal to a. Now what we are going to do is, we are going to substitute this in this. We are taking this as equation 1 and this as equation 2. Substituting the value of a in equation 1, we will get 2c the whole square is equal to 2 into b square, which, so 2c the whole square is equal to 2b square can be written as 4c square is equal to 2b square. So we just got 4c square is equal to 2b square. Now cancelling 2 on both sides, we will get 2c square is equal to b square, which means 2 is a factor of b square. See, the same way b square is equal to 2 into some other number, so 2 is a factor of b square, which also means 2 is a factor of b. So we just found out a has a factor 2 and b also has a factor 2. A has 2 as factor, b has 2 as factor, but a and b are supposed to be coprime numbers. Coprime numbers means they cannot have common factors. Now this contradiction is arising because our first assumption was wrong. Our assumption that root 2 is rational is wrong. Root 2 is actually irrational. Contradiction so the contradiction arises because of a wrong assumption. Hence, root 2 is an irrational number. This is how we can prove root 2 is irrational number or any other irrational number as a irrational number. The only way to prove them is considering them as a rational number, then writing them in the factor form p by q, and from there we are going to bring out some contradiction. So if you're having any doubts, you can always discuss in the comment section. Thank you.